And the second speaker is Juan Carlos Fernández from Universidad Nacional Autónoma de Mexico, and he will talk about the geometric reduction method for semilinear PDEs. Please.
Thank you, Thomas, for the introduction, and also I want to thank Alberto, Francesca, and Benedetta for the kind invitation to this wonderful workshop. And what I'm going to present is actually a bridge between PDEs and ODEs that I have been developing in the last years. And it is really, really related with the existence of what we may call fundamental solutions to some PDEs. So this is a joint work with Jimmy Petran from CIMAT, Oscar Palmas, Monica Clapp, and Alberto Saldaña from UNAM. And what is the problem? I will give a little motivation about the problem. And if we consider this kind of semi-linear problems, one of the first things that we learn in, for instance, PDE courses is that we can look for fundamental solutions. We are now here in RM. So we can try to look for radial solutions. So this is one of the main tools in PDE. And we look for radial solutions. What is this? We consider a solution U given like this composition. So this function is going to be constant on these spheres. And in this case, U is going to be a solution having this form if and only if this B is a solution to this ODE. Okay, we have here something really interesting. Here we have this singular term that is reflected that we have here this singular sphere. Okay, so what we are actually doing is that we are identifying each sphere with one point of this line. Okay, so in many cases, the solutions that we obtain in this way are called fundamental or have really nice properties. For instance, Angela Pistoia gave us yesterday a bridge between the ODEs and PDEs, and she stated a system of some radial solutions to some system of Emden-Fuller type. And this guy here, this guy here appeared. Okay, so this is a kind of radial Laplacian. I want to call it radial Laplacian. So what is behind this kind of reduction? Let us see a little, let's give a closer look to this. So we are considering a function f given like this. And then if we compute the Laplacian of u, we are going to obtain that this is given by b2 prime with this guy, the norm of the gradient, and p prime times the Laplacian of f. So what is behind here? Why can we do this reduction? Because the gradient can be given explicitly as a function of f itself, and also the Laplacian is given by a function of f itself. It is given explicitly like this guy, okay? So we have here that the Laplacian can be written in this form. So we have here what I'm going to call radial Laplacian, okay? We have other examples in Rn. For instance, if we consider Rm split in these two terms, and we consider the projection, the norm of the projection onto the first factor, we're going to obtain a similar radial Laplacian. But we are having here, sorry, this dimension instead of this m, okay? And we also can do the same trick by taking the projection onto the last factor, and we are going to obtain the actual one-dimensional Laplacian. Okay, so what is behind this? We are looking for solutions that are constant, in this case, on cylinders, and we have here a singularity given by this singular cylinder, and we are looking here for solutions that are constant on hyperplanes. But here, as we can see, there is no singularity, and it is reflected that here we do not have singular submanifolds, okay? This is the idea, and we are going to generalize to the setting of Riemannian manifolds. So, what is a Riemannian manifold? Roughly speaking, is a smooth manifold with an interior product that is changing smoothly when we change the points, okay? So we have here some ways to measure lengths and angles in the same way of Rn. And we're going to generalize the idea that we have given for the radial Laplacian, okay? So let's fix a Riemannian manifold, and then we are going to say that a function is called isoparametric if there are some functions A and B such that they make the magic trick. And what is the magic trick? That the Laplacian of f and the norm of the gradient are functions of f itself. So in this case, if we consider a semilinear equation on the manifold and we look for solutions that are constant on the hypersurfaces generated by f, we're going to obtain this kind of equation that it is going to hold on the image of f, and the image of f is contained on R. So we are reducing the PDE into an ODE, okay? And we have here what I'm going to call an isoparametric Laplacian, okay? So this is a generalization of the radial case, and what we are looking and we have here that the solutions to this problem, when we compose it with f, we're going to obtain that u is going to be constant on the level sets of f. So it will be really important to understand the geometry of these level sets in order to get new kinds of isoparametric reductions, okay? So we're going to study a little bit about the geometry of these guys, and we're considering the level sets of f. We have two kinds of level sets. The first are the regular level sets, so they are called isoparametric hypersurfaces, and we also have critical values, and these critical values are called focal submanifolds. One important thing is that if we have an isoparametric function, also the inverse image of the critical values are going to be submanifold. This is not trivial. It was proved by Wang, more or less in 1980s, but it was conjectured by Wang in the 1980s, and it was actually proved by Miyaoka in 2013, I think. So this is not obvious, but we have some submanifolds of the original manifold M given by the critical values. Cartan, more or less in 1938, he tried to classify all the isoparametric functions on spaces of constant sectional curvature. What is this? You fix Rm, the sphere, or the hyperbolic plane, or the hyperbolic space. So a function, or equivalently, and a hypersurface in your manifold is going to be isoparametric if it has constant scalar curvatures. These are the more or less the the values where this curvature is well behaved, something like that. I don't want to get more into this geometric aspect, but what I want to say is that Cartan showed that on Rm, we only have three kinds of configurations. These isoparametric functions are given by spheres, cylinders, and hyperplanes. So what we are saying here, that if we look for more general ODEs, for more general ways to reduce our PDE into an ODE when the manifold is Rm, we are not going to be able to do this because the geometry of Rm, let's say, is really, really poor in this sense. So, and actually, he classified also the case of the hyperbolic space, and it is more or less the same configuration. They are a little bit boring in the sense of the existence of isoparametric functions to do this magic trick to reduce the PDE into an ODE. But this guy here, the sphere, is really, really rich. I will show you that there are many kinds of isoparametric functions to do this reduction, and we can obtain many kinds of isoparametric Laplacians. A little bit about the story of this guy is that if we fix the number of principal curvatures, I don't want to say more about this, but this if we fix and we name it by L, we're going to obtain that this number L is going to be only 1, 2, 3, 4, and 6. Even if the dimension is 1 million, 3 million, we are going to have only 1, 2, 3, 4, or 6 different principal curvatures. So Cartan tried to classify these hypersurfaces and these functions in terms of these numbers. What he got is that he got the classification for the cases L equals 1, 2, and 3. And he showed that actually these hypersurfaces are given by orbits of some groups of isometries. Okay, so these are called homogeneous. But then Oseki and Takeuchi, and later Ferus, Kercher, and Musner, they gave many examples of hypersurfaces with L equals 4, which are not given by orbits of isometry groups. So these are the really striking ones in the geometry of the sphere. And this year, the classification for L equals 4 was over. So this was more or less in 1938, and this is this year that the classification was over. But what happens with L equals 6? Miyaoka said that in the case L equals 6, all the hypersurfaces are given by groups of isometries. They are all homogeneous. But she had a mistake in her proof, and then she published an errata, and the errata was still wrong. So to the date, we do not know whether if the isoparametric submanifold, the isoparametric hypersurfaces are homogeneous or not in the case L equals 6. So this is an open problem, but it is almost done. We have now here that the sphere has a really rich geometry in terms of these guys. So we can consider that we can make a lot of isoparametric reductions. So we can try to look for many kinds of fundamental solutions to PDEs on spheres. So I'm going to give you some concrete examples now And the concrete examples are really, the first example is really easy to understand. We consider the sphere and a point on the sphere, and we consider this polynomial. And what we're actually taking is, we are taking 2 points, 2 antipodal points, and we are considering these parallels. So the parallels are going to be the isoparametric functions, and these guys here are going to be the focus of manifolds. I want to recall you that the focus of the singularities in terms of submanifolds are going to give some singularities of your Laplacian. So it is important to remark that we have here exactly 2 focus of manifolds. Then another example that has been really used in the literature of PDEs is the following one. If we consider that the sphere is embedded in Rn+1 and we decompose Rn+1 as Rk times Rn, and we consider this function, what we are obtaining here is that the isoparametric hypersurfaces are given by products of the spheres, and the focus of manifolds are given by each of these spheres. Again, we are having 2 focus of manifolds, and I will see that it will be reflected in 2 singularities of the Laplace operator that we are going to obtain. And these kind of symmetries were used, for instance, by Ding in 1986 or 1984. I don't remember exactly, to obtain the first sign changing solutions to the Yamabe problem. And later, Thomas, Tobias Beth, and Schneider, they used the same symmetries to obtain the same result for Q curvature problems on the sphere. So they produce the first examples of sign changing solution of Q curvature problems, which are problems related with polyharmonic operators. Now, these 2 examples, L equals 1 and L equals 2, they are available in all the spheres, but there are also other examples which are a little bit esoteric that are given in some dimensions. And these are given by what is called now Clifford systems. What is a Clifford system? It's something that I really do not understand, but I will try to say more or less what this is. This is a collection of some symmetric operators on Rn+1 satisfying these properties here. So these properties here may seem a little weird, but if you have played a little bit with quaternions, you can see that these are the properties given by the quaternions. So the people who is related with algebra and all that, we can say that the Clifford systems are representation of Clifford algebras on Rm+1. So in this case, we can consider another kind of isoparametric functions that are given by this kind of polynomials. We have here a 4th order polynomial, and we have also here something that is a order 2, but we have here this interior product, so it is of order 4, and is the order of this L. So we have here some concrete examples, and if you want to look for solutions to a PDE on the sphere having this geometry, you're going to obtain really strange level sets. Why? Because actually the level sets are tubes around what is called Clifford-Stiefel submanifold. The Clifford-Stiefel submanifolds are some quotients of some orthogonal groups, and they are a little bit they are really interesting and not trivial. So you can obtain some some really rich geometry using this kind of hypersurfaces if you look for the solutions to the reduced ODE. So now I want to focus that now that we have many examples on the sphere, I want to focus how to reduce the PDE into the ODE. A deep result of the theory given by Munzner is that if you consider your favorite isoparametric hypersurface on the sphere that is going to be part of your level sets, there is going to be an isoparametric function that is actually a polynomial that, as the ones I given before, in such that way that the image is this interval -1, 1. All the hypersurfaces are given by the inverse image of T, where T lies between -1 and 1. Actually, F -1, these guys are the focals of manifold. So these are the given by these not well behaved critical values. And we have exactly 2. And what it is more important is that the gradient and the Laplacian are given explicitly by these functions. So the gradient is given by this explicit quadratic function, and the Laplacian is given explicitly by this linear function. And here we have some constants. These constants are geometric constants I don't want to talk about. But in this case, if we consider, since we are lying here in -1, 1, we can consider this further composition, and we can look for the Laplacian of a function W from 0 pi composed with Q, and we are going to obtain a really nice Laplacian. This Laplacian is going to be given by the Laplacian, the one-dimensional Laplacian, and another term here. And this another term is given explicitly by something, a constant times cosine minus another constant divided by sin of t. And t is now here on 0 pi. So I was saying before that we have 2 focals of manifolds, and it is reflected here that this operator here is singular in these 2 values because sine is going to explode on these 2 values. So we are obtaining some kind of singular operators here. So now I'm going to give the application. The first application that we use, that we obtained, is that if we consider some kind of Yamabe problems, these are the Yamabe problems, these are a Laplacian plus something that is going to be constant now, and we have a power nonlinearity here given by P greater than 1. So we are looking for solutions to this problem on the sphere. Why is this important? I want to recall you really quick what the Yamabe problem is. And the Yamabe problem is the following one. If you have a Riemannian manifold with a really nasty scalar curvature, one looks for another metric which is conformal. That is, if we can multiply this metric by some positive function in order to obtain a new manifold in such a way that the scalar curvature is now well behaved. These have really nasty scalar curvature with this really curved, and this guy here is really nice because it's not that curved. It has constant scalar curvature. So this problem, this geometric problem, is translated into a PDE, a critical exponent PDE actually, where RG is given by the scalar curvature, okay? So we have this problem that is a fundamental problem in geometric analysis and PDE and all that. And we restrict to this kind of problem. This is the Yamabre problem on the sphere, but we are allowing the subcritical, critical, and supercritical cases also. So we are going to what we actually have is that U is going to be a solution having constant, which is going to be constant on the level sets of this isoparametric function, this, if and only if W is a solution to this problem. We have here then this part of the nonlinear terms, and we have here the isoparametric Laplacian, okay? So we have here an ODE, but this ODE is not as easy as it seems because, as I have said before, this H is singular on 0 and pi. So this is a singular ODE. The first result I want to present is that we obtain a kind of prescribed geometry and prescribed qualitative behavior of the Yamabe type equations. So if we consider your favorite isoparametric function, isoparametric hypersurface on the sphere, I have said before that there are lots of them, and we fix a number k, what we actually obtain is that this guy is going to give some number which is a critical Sobolev exponent in another dimension, in such a way that if we consider this subcritical case, even if this is subcritical, this P could be subcritical, critical, or supercritical above the critical exponent, the critical Sobolev exponent on m dimensions. What we obtain is the following. There is going to be a solution to the Yamabe type problem having exactly k nodal domains. And also the connected components of the level sets are going to be all isoparametric hypersurfaces, and they are going to be all diffeomorphic to S. Actually, they are going to be what is called parallel. You only translate in a normal direction your manifold. And so you're prescribing the geometry of the solutions, and also you're prescribing the qualitative behavior in terms of the number of nodal domains. What we have done, what is the trick behind this? Behind this, we have that we reduce to an ODE. So we are considering an ODE here from 0 pi, and we are looking for solutions having exactly k minus 1 zeros. So we are going to obtain exactly k nodal domains. Yes. And what are the techniques behind this? We use what we call a double shooting method. We shot solutions from this side, but as it is singular, they may explode here. And also we shot solutions from this side, but they may explode here. So we are trying to look for right, what is called this, the initial conditions in order, initial and final conditions in order that the solution is well given. Yes. So this is the more or less the idea that is behind this kind of result, and we perform a really let's say, how do we say that we have real problems and real geometric problems and technicalities to to see that the phase plane analysis was, well, we make a careful phase plane analysis to obtain this. But we actually generalize these kind of problems to another kind of equations. And we now consider the semi-Riemannian case. This is new. So a semi-Riemannian manifold is the same as a Riemannian manifold, but we have now here an inner product that is not definite positive. So for simplicity, you can think that this is a Riemannian metric, and if we consider some parts of the coordinates to be the time components, and we give us a minus sign to this, we're going to obtain more or less a semi-Riemannian metric. What is important here? In the semi-Riemannian setting, we have a semi-Riemannian Laplacian. And what is the Laplacian? It's actually the same as the Riemannian Laplacian, that is the divergence of the gradient. But now it is called the D'Alembert operator. Why it is called like this? Because if we fix the case of the Lorentzian setting, we are going to obtain that the Laplacian is given by the wave operator. And if we consider the general case, the general semi-Riemannian setting, this Laplacian is going to be a competition between two Laplacians. One Laplacian in the time variables and another Laplacian in the space variables. These are called ultrahyperbolic wave operators, and these are really complicated to handle. So what we have done, we saw that all the theory of the isoparametric functions on pseudospheres work as in the Riemannian case, and we study the Yamabe type problems for pseudospheres. The Yamabe type problem is again this kind of equation, and it is going to give you exactly the same as before, but now your metrics are not real metrics, are semi-Riemannian metrics having constant scalar curvatures. You can generalize all these concepts to the semi-Riemannian setting. And now this guy is the sphere, but with this semi-Riemannian metric. And with semi-Riemannian setting is what we obtain is that it is given, this equation is given like this equation. So your sphere is now this hyperboloid. I think it's called hyperboloid. So we study this Yamabe problem in this setting, and also we have all the theory of semi-Riemannian isoparametric manifolds, and we obtain the same result, but now we obtain blowing up solutions having a prescribed geometry and a prescribed number of nodal domains. So if we look for the solutions, now we have 0 pi, we have the same as before, but now after these levels, the solution is going to explode. And it is reflected here by saying that there are two kinds of isoparametric submanifolds in such a way that if we are close enough to this manifold, the solution is going to explode. We believe that these manifolds are minimal. We have improved it, but we believe that it is possible. And I have no more time to explain something, but I want to say only that we can also play these kind of tricks for polyharmonic operators on spheres. So we have here a polyharmonic operator, and as we have this Laplacian, we can make this PDE reduction method because we are going to obtain a isoparametric polyharmonic operator on 0 pi, again 0 pi. And it is given by the isoparametric Laplacian plus something. And to finish, just a few seconds, we applied here this kind of problem to see that a Sobolev space with symmetries is actually isometric to a weighted Sobolev space on 0 pi. Okay, so all these kinds of symmetries that Ding and Thomas, Tobias, and many people have used are just we are just playing in something with one dimension. So these are the references here, and thank you very much for your attention. I hope you have enjoyed this talk. Thank you.